Hello, my name is Caroline,
And my name is Melissa.
and we're going to be talking to you guys today about a personalized curriculum system for engineering students. An interest in the engineering field has increased greatly over the past decade in response to technological advances and increased student exposure to STEM subjects. As a result, many more universities are creating new programs and/or improving on existing programs to address these needs. However, what many curriculums still lack is customization based on students' needs, skills, and career objectives. This is the problem that we seek to address briefly in this project. We have designed a new algorithm that offers a suggested academic trajectory to students based on their skills, career objectives, and the successful academic path of past students with similar interests. The inputs we used in our algorithm consist of data collected from over 10,000 past students, in addition to data from current students. The output of the algorithm is a personalized curriculum which offers suggested course groupings per semester. It also offers suggested electives to the student based on their career objectives. Our objective was to identify a sequence of courses with the highest overall average grade. The constraint was that the algorithm could not suggest those courses which had already been taken in a prior semester. So what is the importance of this problem? Well, if you have a targeted curriculum, that means two things: time well spent and money savings. As far as time well spent goes, some students may be returning to school to further their education, and they may have families and/or full-time jobs to tend to, so time is of the essence and shouldn't be spent doing coursework that will not be fruitful to their career objectives. As far as money savings, tuition is becoming more expensive every year, and students graduate with significant student loan debt. Spending less time in school means less money spent on tuition. Having a targeted curriculum also means that students won't be wasting money on classes that they don't need. Another thing that serves as important to this problem is that if students are pursuing what they love, their career goals are more likely to be met, and they'll also be contributing more effectively to society because they're doing what they are passionate about. Some of the associated challenges that we encountered when designing this algorithm were both technical and non-technical. From a technical perspective, one issue that we face is due to differences in data types and depth complexities in the database. Depth complexities refers to how many inputs we should use to make our algorithm effective and efficient. This in turn also takes into consideration that different inputs will also vary in data type. So selecting the best inputs for our algorithm has been one challenge. Another problem that logically follows suit is how do we, upon choosing our inputs, decide how strongly to weigh those inputs so that our algorithm is not prone to biased outcomes. Now, from a non-technical perspective, apart from having to rewire how people think about engineering education, which encompasses many bureaucratic hurdles, there are many other considerations at hand. To name a few, the costs of implementing these changes would be far more in an underserved community than it would be in a more affluent one. There is also the issue of assessing and/or standardizing the skills needed for specific jobs. For example, some computer science graduates leave school and either don't have experience in a variety of in-demand programming languages, or their skill level may be too basic. So the challenge is in partnering with businesses and assessing real needs of students so that they graduate with a real-world know-how, rather than a generic understanding of the subject matter. Some of the research that we came across when trying to design this algorithm, we found that most of them focused on the students' learning styles and enhancing their education to suit those learning styles. And they also addressed the method of instruction, so whether it was web-based or an in-person type of instruction. The novelties in our approach is that it seeks to tie the student's skill set and career objectives with their academic trajectory rather than focusing on learning styles. By doing this, we feel students would have a better chance of tailoring their education to suit what they're good at, as well as what they want to do career-wise. This is one of the novelties in our approach. Another novelty is that it is specific to traditional engineering curriculum, whereas other approaches are catered to personalizing curriculum for web-based environments. Yet another novelty is how our algorithm is designed. The algorithm considers not only the skills and career objectives of current students, but also the academic trajectories of past students whose skills and attained career is similar to the current students. We believe this will give the current student a good idea not only of what courses they should take per semester to achieve their goals, but also of how well they can expect to perform in that class grouping.
So our core algorithm can be broken into two parts, pre-processing and curriculum building. In pre-processing phase, the goal is to get a set of past students whose skills and career goals closely align with our current student. Given our current students' skill scores and career objectives and a set of past students with skill scores and post-graduation careers, we match the current student with past students whose post-graduation career match our student's career objective. We then compare each of the current students' skill scores against past students' skill scores. If the difference between scores is less than the provided threshold for all skills, then the past student is added to a list. Once all eligible past students have been iterated through, then the list of students is sent on to build the curriculum. So this curriculum building algorithm is the meat of our project. Given a set of past students whose skills and careers align with our current students, we want to output a set of semesters with a group of classes that result in the highest cumulative grade. We iterate through each semester and compare the set of classes past students have taken. If there is a set of students who took the same classes, we take the average grade of each class. We do this until we only have unique sets of classes. We then calculate the semester grade of each set of classes. From here, we select this set of classes for a student's semester and continue the algorithm until all graduation requirements have been met. After the first iteration, we check to make sure we do not select sets of classes that have been already added to the current student's curriculum. By utilizing past students' data, prereqs are already accounted for since past students could not take classes they are not allowed to take. Our approach stands to offer quality and a more refined sense of purpose to a student's academic pathway. However, time constraint has been a significant past constraints have been a significantly limiting factor in the process of designing our algorithm and approach. We've not been able to implement our approach to test this performance, so our validation is limited to logical reasoning at this point. Conducting an experiment of this magnitude would take, at the very least, several years to aggregate and analyze the necessary data before we can affirm or deny the claims we've made here. Another weakness to our approach is that we have to make a lot of assumptions due to time. Some of these include all students taking the same number of classes each semester, as well as not having any extraneous circumstances such as medical issues and personal problems. These assumptions can make the algorithm not be applicable in practice. An analytical evaluation of our approach consists of measuring the success rates of students, both past and present. We evaluate students' academic performance and whether their post-graduation career identified with their course trajectory. We also assess any changes past students may have made along the way and how those changes affect their academic pathway. For instance, if they decided to change their career objective, what changes were made to the courses they took to realign the course path with the new career choice? Does this change add to or reduce the number of classes that will need to be taken? We also want to consider what factors influence such changes, especially if the changes result from a good or bad course experience. Conclusively, we believe that through examining the aforementioned questions and patterns of past students, our algorithm can successfully recommend course groupings that make sense with current students' end goal. It should be noted that the course groupings presented by our algorithm are neither exhaustive nor are they final. The final decision is made by the student and their advisor. The algorithm's output should serve as a suggestive input to the student and the advisor's final decision. Thank you very much for listening to our presentation.